Hey everyone, welcome back to more calculus. Today we're going to continue with areas in a plane using integral. So let's go ahead and check it out. Okay, with a shape evoking a flying clothes iron, Slave 1 is one of the more interesting crafts in Star Wars. I'm sure you've seen this already, but if we look at the bottom of Slave 1, this is what we're going to use for our area. So we've got a shape where the left side of this is functioned by x equals 1/2 y squared, and the right side is modeled by x equals 8 minus y squared. So this is kind of problematic with the way that we currently look at area, because the top function here and the bottom function here are actually the same function. They are both x equals 1/2 y squared. Over here, on the top function changes to the top half of 8 minus y squared, but the bottom function is the same function, x equals 8 minus y squared. So this is kind of problematic for us. So there's something that can help us is that if we decided to look at this sideways, like literally turn your head and look at it sideways, you can see that the function on the right side, this 8 minus y squared parabola, that's always on the right side of this function. Likewise, the left side of this function is always x equals 1/2 y squared. So if we approach these as functions of y instead of functions of x, then we'd have a much easier time of doing this. And in fact, we have this entire thing about areas on curves, looking at everything sideways in terms of y instead of in terms of x. So this time, a is a lower bound, b is the upper bound, f of x or f of y is the right function, and g of y is the left function. So it's integral of right minus integral of left evaluated from bottom to top. Now, let's see what this is. Functionally speaking, there is no difference between computing areas horizontally and computing areas vertically. In fact, if you want to rewrite this entire thing as instead of x equals f of y, rewrite it as y equals f of x, everything will be fine. Just switch all the x's and the y's, and you can compute this normally. But we're not going to take that approach. We're actually going to go f of y minus g of y. So looking at the function that or the graph of the function that we were just looking at, we can see pretty plainly that the function on the right side is the green function, 8 minus y squared, which means the function on the left is that blue function, g of y is going to be 1/2 y squared. Now we have no idea what these intersection points are up here and down there at the top and the bottom. So we're going to have to solve for that. So we'll solve 1/2 y squared equals 8 minus y squared. And we keep solving this. We've got 3/2 y squared minus 8 is equal to 0. Multiply everything by 2/3, and you get y squared minus 16/3 equal to 0. And ultimately, you get y equals negative 4 root 3 over 3 and positive 4 root 3 over 3. So, there was a space over here for me to write that. I might as well write that. Y have 1/2 y squared equals 8 minus y squared. So a is equal to negative 4 root 3 over 3, and b is positive 4 root 3 over 3. So I'm really not doing you any favors with these numbers, am I? These are pretty intense looking. So how about we put this in here? Negative 4 root 3 over 3, positive 4 root 3 over 3. We said the left function was 8 minus y squared. We said the right function was 1/2 y squared. And we're set to integrate this. One of the things that might help us make this easier to integrate is if we notice that the area from the bottom half is exactly the same as the area on the top half. So what I'm going to do is I'm going to cut in half and double is basically what I'm going to say we're going to do. Cut in half and double. So what that means is I'm going to double the integral, but I'm going to cut the area into just the positive half, 4 root 3 over 3. Now this is kind of desirable. I think you could see why, because there's no more negative numbers to substitute into our antiderivative. And things get a little bit easier this way. Sometimes I'll say that I'm just taking advantage of symmetry here. Either way you look at it, this is a really great practice for you to use. So what is that? 3/2 y squared, is that correct? Okay, let's get our antiderivative down. Okay, 8x minus 1/2 y cubed. One thing that you can do, which might make calculation easier, I don't know how you feel about it, but you can factor and also distribute into this if you like. So I'm going to distribute into this. I think that might make my calculation a little bit easier. That's going to be equivalent to 16x minus y cubed from 0 to 4 root 3 over 3. I think you can see why that's going to make things a little bit easier. Oh my gosh, this should be a y. Oh boy, and then all of that, we've got minus 64 root 3 over 9, and all of that gives us 128 root 3 over 9. So that's our integration. Of course, now we have to write a summary. So the area of the bottom of slave 1 is 128 root 3 over 9 square units. Let's see what we have over here. Sometimes you're going to find that boundary curves change throughout the region. So in this case, you're going to partition into subregions, and that correspond with a change in boundaries. So I'm looking at this shape over here, and first of all, this would be really easily done if you just did right curve minus left curve. Some of you will feel very comfortable about that because the right curve is always going to be y equals x minus 2, and the left curve is always going to be y equals root x. But if you feel like, or if you would rather, we can turn this into two subregions over here, region A and region B. Now region A goes from 0 to 2, and then region B goes from 2 to 4. So now let's just look at region A. In region A, that top curve there, that was, and I'm forgetting, it is root x. And the bottom curve is 0 because it's the x-axis. A is 0 and B is 2. So this becomes the integral from 0 to 2 of root x minus 0. That's going to give me an area of 4 root 2 over 3. Here's me working out the antiderivative. Region B, let's take a look. That top curve right here, that's root x. That bottom curve, that was x minus 2. It's nice to think in terms of this is the linear curve, so we know we're looking for a linear function. Lower limit is 2, upper limit is 4. So this becomes the integral from 2 to 4 of root x minus 2. Keep those parentheses there because that's going to, affect your answer algebraically. Integrating that entire lot together, you get 10 minus 4 root 2 over 3. Here's my work with the antiderivatives on the right side. And now you just have to add those two results together. So area of A is 4 root 2 over 3. Area of B is 10 minus 4 root 2 over 3. And it looks like our answer is just going to be 10 over 3. So I can't emphasize enough for you that if you had decided to approach this as the right curve minus the left curve, you would have saved yourself a lot of calculation. But, totally up to you how you decide to do these areas. Most often there is a more expedient way of doing things. So there is some wisdom in choosing which of those to use. In any case, we can move on to our important ideas here. And our important idea is the area between curves. If you have continuous functions, then one way to approach it would be just the integral of the right curve minus the left curve. And finally, whenever a boundary curve changes, you're going to have to divide the region at the places where the top curves and the boundary curve and the bottom curve changes, compute multiple integrals, add all those results together. For our check your understanding, we're going to find the area of the region in the first quadrant bound by y equals cosine and below by the x-axis and also by y equals x minus 1/2. So we're in the first quadrant only, and we're bound by the x-axis. Let's graph this since this is a calculator question. And this time I'm going to change this. I don't want the standard window because I only want to look at the first quadrant. So let's make this negative 0.5 to 10. And then the y min will make that also negative 0.5. And that'll just give me the 10 by 10 first quadrant look. And then push graph. Here's what we got. Ooh. Okay. And right. So I'm thinking we're only looking at this region right here because this is the only region in curved that is enclosed by the axes and the first quadrant. So it looks like we can look between 0 and 1. So let's go ahead and change our x maximum. We'll make that 1.2, and we'll make our y maximum also 1.2. Yeah, that looks a little better. That's that cosine function. And then here's that linear function. So let's figure out a couple things. What are all of the intersection points here? So the first one, obviously this is 0, 0 here. Let's just import this into the Word document. I know I said Word document, but this is actually a OneNote document. All right, I'm going to shade the region in. I'm going to shade this in blue. Now, a few of these corners are pretty easy to know. This one right over here, that is 0, 0, of course. This one over here, if we know anything about the cosine curve, we know that that is 0, 1. And this over here, this is a little bit more difficult, but that's when the linear function is equal to 0. So when is 0 equal to x minus 1/2? Of course, that's at x equals 1/2. So that's 1/2 comma 0. And the last one over here, this right there, that's going to be when cosine x is going to be equal to x minus 1/2. Now that's not easily gotten, so we'll go back to our calculator and we'll use our calculator to find that intersection point. And second, calculate intersection. It's usually my habit to start off by cursoring over to the point of intersection. So I'm going to just cursor over there. And am I on the first curve? Yes, enter. Am I on the second curve? Yes, push enter. Scroll right on top of it, push enter, and that is 1.0201. So all of you who thought that that intersection point was 1, you were wrong. So even if it looks like it's 1, you do want to just solve it to make sure that you know what that intersection point is. I've taken away a lot of points from a lot of really otherwise brilliant students because they trust their eyes a little bit too much here. So let's go ahead and write down that intersection point. And we have all of our intersection points. Now we're going to divide this into subregions. So I think, we'll call this region here, we'll call this region A, we'll call this region B. And I think I got this wrong. This was 1/2. Okay, let's now figure out the area of A, region A. The area is the integral from 0 to 1/2. The top function here is the blue line, which is cosine. And the bottom is the x-axis, so that's 0. Of course, you don't have to write 0 there. And we'll calculate that now. What's the integral of cosine from 0 to 1/2? Integral from 0 to 1/2 of cosine x dx, 0.4794. Now we'll find the area for region B. Okay, the lower limit is at 1/2. The upper limit is at 1.02181. I just realized that I forgot to save that into my calculator. But I have 5 digits already written down. That should be enough for me to get an accurate result. Now the top curve is still cosine. The bottom curve is now x minus 1/2 dx. So let's put that into our calculator. First of all, let's make sure that x didn't change. Oh, 1.021. Oh, yes. Okay, let's save that as b. Store that as b. So we're going to now integrate from 1/2 to b. The function on top was cosine x. The function on the bottom was x minus 1/2 dx. All right, 0.23748. Finally, the area is going to be equal to 0.447942 plus 0.23748. Coming back to my trusty calculator, I'm just going to grab all those numbers and add them together. So the first one here is this 0.479 plus, scroll up to the 0.237, and we'll add those together, 71691. So we've got the area is 0.71691 square units. Okay, that pretty much does it for today. Hopefully this is good news for you, or, we've got some good stuff here. Two things today. Remember, if we're doing the area, we can go right curve minus left curve. And if we have multiple regions, we just find the area of each individual region and add them up together. Now, that's a lot of strategies that we've come up with in order to solve these area problems. It is up to you to figure out what is the best strategy for you, which strategy is the one that will get you to the area the fastest. With that, I'll see you guys later. Have a good rest of your day.